So Pedro, are you ready?
Mm-hmm.
Okay, so welcome everyone to the algebra geometry seminar. Today our speaker is Pedro Nunes from here, and he will talk about indecomposability of Dirac categories of hyperelliptic manifolds. I think.
Mm-hmm.
Yeah, please.
Yeah, so thank you very much for the introduction, and thanks for giving me the chance to speak here. Yeah, so that is the title. Oh, there's a clock somewhere? Yes, okay. Dirac categories of hyperelliptic manifolds. And yeah, so the title is based on joint work in progress with Peter, Bellmans and Andreas Demleitner. Right, and in fact, I want to use this topic as an excuse, so to say, to talk more generally about birational geometry and derived categories and their relation, which is some sort of broader topic that I'm interested in. So the plan would be the following. So first, derived categories and birational geometry. Second, more precisely, MMP. Semi-orthogonal decompositions. So SOD stands for semi-orthogonal decomposition, and later we will explain what this means. MMP, minimal modular program. Right. And then finally, we will come to this indecomposability. Question. Okay. And the idea is that hopefully this first part and maybe also the second one is more introductory and not so many details, but rather an overview that hopefully is accessible to people, even if you haven't seen derived categories before. But I think most people here have been in seminars on derived categories or, yeah, but anyway. Yeah, so if I say something that you don't understand, please interrupt and ask about it. And also if I write something that doesn't make sense, also interrupt and ask about it, because maybe I really just wrote something which is wrong or something. Yeah, so feel free to ask questions anytime. Good. So let's start with the first part. Derived categories and birational geometry. And since I'm not going to give too many details, I'll give two references in case anyone wants to see more details. So references. So we have Huybrecht's book. So this is Uriyamukai functors in algebraic geometry. And the second reference is a paper of Kawamata. 17, so it's birational geometry and derived categories. And this is by Kawamata. Okay, I hope my letters are readable. Right. So if anybody wants more details, I think those are good references. So let's start talking about the topic. So we have a smooth projective variety. And let's say it's over the complex numbers. And now we want to do some birational classification. So we want to look at some invariants of this guy. And one possible invariant we could look at is the category of coherent sheaves. And this is a very nice abelian category. But the downside is it determines X. And why do I say this is a downside? Because the whole point of an invariant is that you want to make your life somehow easier, right? And then you want to distinguish things with some invariant that is easier to compute. But this invariant is just as hard to compute as X itself because it determines X. So not so nice. And a solution we can try is to pass to the derived category instead. And now this guy is triangulated category. And it doesn't always determine X. Yeah, so not always. But we will see that it's actually pretty close to determining X. Okay. Right. So most of the talk will be devoted to talking about derived categories of varieties and this kind of semi-orthogonal decomposition. And these are the compositions of this triangulated structure. So I think it's important to review what it means to be triangulated. So let's do that now. Okay, so definition. A triangulated structure on an additive category A is given by an additive autoequivalence. So something like this. And this is called the shift usually. Or topology like the suspension, something like this. And also some collection of distinguished triangles, which are diagrams of the form A to B to C to shift of A, satisfying some axioms. Okay. Right. And maybe I will later, or okay, maybe I can say it now. So this category here, coherent, is an abelian category, which means we can do homological algebra. And if we want to compute the invariant of some sheaf or something like this, we can take a short exact sequence and then apply some functor or something like this. And this guy here is not abelian anymore. So, but we still want to do homological algebra. And this kind of distinguished triangle is going to make up for this loss of short exact sequence. So kind of a replacement for these things. Yeah. Okay. And we want to talk about the compositions of this structure. So we need to say what the pieces are going to be. So full additive category. It's called triangulated subcategory. If it is shift invariant, which means so for every A object in A, then T of A is in B, if and only if A is in B. And also, if whenever 2 out of 3 objects in a triangle are in this subcategory, then so is the third one. Yeah. So it's a bit like asking it to be closed under extensions for abelian categories. Okay. So these are the two important definitions, because again, we're going to be looking at this kind of structure, and we're going to be looking at the compositions of this structure into pieces which are of this kind. Yeah. Okay. And since I'm going to be talking all the time about triangulated categories, I should remark I think it's unfair if I don't do it, that triangulated categories are not so good. So I can say extra structure, not a property. And this is bad. So being abelian, for example, or being additive is a property. So if you're given a category, then it makes sense to ask, is it abelian or not? That makes sense. The answer is yes or no, but it doesn't make sense to ask whether a category is triangulated or not. You have to specify some extra data. And this leads to many problems, but luckily there exist some fixes. And maybe if anybody's interested in this, just this morning, there was some lecture notes of someone in Academia Sinica here. So you can have a look at Khan's, I forgot the title. It was uploaded this morning. Lecture notes on algebraic stacks, I think. Yeah, so in this case, the fix that they use is infinity categories, which is like a more modern fix. Okay, but this is just to say that, yeah, I'm going to be talking about triangulated categories all the time, but it's actually not so cool. But luckily there's a fix, so you can pretend like it's fine. Good. Okay, any questions so far? Let's see. Okay, so this was about triangulated categories in general, but we want to talk about the derived category. So for the derived category of coherent sheaves, a more concrete description. So the objects are complexes of coherent sheaves. Well, with bounded cohomology, but let me just be a bit imprecise. So these are just sheaves together with sheaf morphisms. And whenever you compose two consecutive ones, you get 0. So these are the objects of the category. So that's good. And now the shift of some complex is given literally by something called the shift. And this means you take the complex and you shift it. So which means f of 1 on degree I is given by f of I plus 1. And then the differential is minus the, yeah, something like this. Okay. So we have the objects in the category. We have what the shift will be because we're describing the triangulated structure. Now we want to say what the triangles are. Distinguished triangles are such that every short exact sequence of, I should say, complexes of sheaves gives you a distinguished triangle. And this is the important part. So there's a collection you can explicitly describe, but the important thing is that you can now really replace short exact sequences with these triangles. Right. And finally, we have the morphisms. Are such that if we now take morphisms in dvx of between f and g, let's say, and I should put here a shift. This is isomorphic to extensions of. So the classical higher derived functor of the home functor, if these are sheaves, let's say, and this means 1 to the power I. So we just do this functor as many times as we need. Okay. And this property is very nice because, I mean, okay, so one can also describe the morphisms, but the description is a bit more complicated. But this property is nice because, for example, let's say you want to compute the morphisms, let's say something like this. Now you ask yourself, what is this group of morphisms? And first thing you can do is you can pretend that everything is a vector space. So it's a bit brute. You shouldn't quote me on that. But so you can now take the dual here and take the product with the dual of this vector bundle if you want. And now we can apply the thing we just said. So this is going to be, sorry, xi structure shift into this guy. And then this x guy is just the same as the hix of E. So here it's because so this is the high derived functor of this guy, and this is the high derived functor of this other guy here. And they're just isomorphic functors. So you see that if you want to show that there's no morphisms or no non-zero morphisms from this guy to this guy, at the end of the day, you only have to compute some cohomology group. So that's, even if the morphisms are very complicated, in the end, you can do computations with them. Yeah.
Sorry, just the object should be in DBX should be complexes with bounded.
Yeah. And it's also, yeah, you can say complexes not necessarily of coherent shifts, but whose cohomology shifts are bounded and coherent. Yeah. Yeah, I mean,
It's okay.
yeah, I'm not sure which is the best. Yeah, I'm just gonna write here bounded complexes. But yeah, you can get away with saying that they are complexes, maybe unbounded, such that the cohomology is bounded. And yeah, thanks. Right. Maybe I'm too fast, I don't know. So any questions about this? Okay, maybe it's better like this. So now we can come to some facts about the derived category. So the first one, we said this guy doesn't always determine X, but it is pretty close. So in fact, if you look at this guy together with the tensor structure, this determines X already. It's pretty close to determining X. And for the same reason that we don't want to look at coherent shifts, because they're too fine as an invariant, we also don't want to look at the derived category together with the tensor structure as an invariant because it determines X already. Yeah. That's the first thing. And another important thing is that Serre duality translates into the existence of a Serre functor. Serre functor on dBx. And let me define now what this is. So this is a additive. Here I'm giving a slightly wrong definition because I should be saying a C-linear or K-linear, but let's say it's an additive functor, autoequivalence. We can denote it like this. With the following property, such that ohms from A to B are bifactorially isomorphic from ohms to B to the Serre functor applied to A, and then you take the dual. This has to be bifactorial. This is for every A and B here. Right. So Serre duality is some very nice theorem that we have in algebraic geometry. And when we look at the derived category, this theorem translates into the existence of such a functor. And now this functor is just something defined purely in terms of category theory, or just in terms of home functors and things like this. Yeah, so in the case of a variety, we have Serre functor is given by tensoring with the canonical line bundle, and then shifting by the dimension of X. Yeah, but again, so this functor is now defined only in terms of category theory. So here there's no geometry, no nothing. You can define this for an arbitrary additive or k-linear category. And moreover, these Serre functors, they are uniquely determined already by this property. So if you have two Serre functors, they have to be the same. So some consequences that this has. Well, the first one is that we can recover the Serre functor from the derived category. And the Serre functor in our case is given by this. So everything we see here, I mean, this is not true, but more or less we can recover this information from the Serre functor. So dbx determines dimension of X. And then we finally see some relation with birational geometry. So maybe this is one of the first birational invariants you can think of for a variety. And the derived category determines this invariant. And moreover, dbx also determines the canonical ring. Something like this. So this is another very important birational invariant, and the derived category also determines this. And the reason, okay, it's roughly speaking because you can see it there, and this is encoded in some categorical information. Right, and finally, from this last part, we see if kx or minus kx is ample, and then we can recover the whole X. Determines X, because X is determined by this canonical. And this is called Bondar-Orlov reconstruction. Right, maybe I should say, so this one is called Balmer's reconstruction, and the one with coherent shifts is called Gabriel's reconstruction, I think. Right. Yes. Yeah. I should put it here. Yeah. Maybe I take red. That's probably hard to erase. Okay. Yeah. Smooth projective variety, irreducible variety. Yeah. Yeah, thanks. Okay. Any other questions?
So even for the reconstruction result, you need smooth projective or?
Sure. So I mean, if this is ample proper is enough.
Yeah, but for the tensor, I mean, for the tensor.
I know for this you don't need smooth projective. For this you don't need anything. I think quasi-coherent. Yeah. So whenever you have a tensor triangulated structure, you can associate some spectrum of this triangulated structure or something like this. And then I think for maybe to be safe, quasi-coherent, quasi-compact, quasi-separated schemes.
Okay, so quite general.
Yeah, this one is very, very general. This one, I'm not so general, but I'm not sure what is exactly there. Yeah. Right. Okay, and I think this is all I wanted to say about the part one, derived categories and birational geometry. So yeah, the takeaway message is that this derived category does determine quite a bit of the birational geometry of X. And this is mostly thanks to this Serre functor, so mostly thanks to Serre duality. Okay. Right, so now we have seen some very, let's say, mild relation between derived categories and birational geometry, but now let's see something more concrete. And this is the relation between minimal model program and these semi-orthogonal decompositions, which we'll define later. Sorry about that. Yeah, so let's say we are running some MMP, and to make it simpler, we do it on surfaces. So we have some surface S0, we blow down some curves, and we end up with some surface Sn, maybe, yeah, which is in some way the simplest representative in the birational equivalence class. So let's say it's non-negative Godard dimension. And what we're doing here at every step is we're just blowing down some curve. And in fact, when you blow down, okay, maybe we say the other way around, right? When you blow up a curve, when you blow up a point, you're just replacing a point with some P1, which is like a sphere. So it's like a two cycle in homology. So you see that some of the invariants of this guy are going to be more complicated than the invariants of this guy somehow. So you maybe expect that the derived category here is bigger than this one. I mean, this is very sketchy, a very big stretch, but in fact, this is true. So the derived categories are decreasing. This is the smallest one. So at least for surfaces in this process of blowing down curves, we're reducing the size of the derived category. And by this, of course, I mean that there is some fully faithful functor here. Yeah, so it's not like this is a subset of this or anything, but so you can see this via some fully faithful functor as a subcategory of this. Right. So we have this kind of parallelism, and maybe here it's just a coincidence for surfaces, but why should this be the case? So morally, both things are very related to the canonical divisor. So KS maybe, let's say. Right. And along these lines, we have the following conjecture. So this is Kawamata decay hypothesis. So we have X, Y, C, smooth projective varieties. And we have some diagram like this. With the following condition. So we have to somehow relate the canonical divisor. So let's say the pullback of the canonical on X plus some effective divisor. So this is all the coefficients are non-negative, is linearly equivalent to the pullback of Y. So let's say you have this kind of condition, then Kawamata conjectures that the derived category of thing on the left is going to be subset of the derived category of the right. And you see this thing here is a particular case where you take here G equals to the identity, and you're just blowing up things, and then the blow up contains the smaller thing, the blow down. Yeah. So this is I guess one can say, one of the leading conjectures in these relations between birational geometry and derived categories. And the conjecture is bigger than this. So it also includes the case in which there's no E here, and then you have an equivalence. But yeah, this is the one that we want to focus on. So is the statement of the conjecture clear? So feel free to interrupt anytime. Okay. Right, so we have this conjecture, and now let's finally start talking about the compositions. So far we've only been talking about inclusions of categories, but the following. Whenever we have such an inclusion of derived categories of varieties, smooth predictive varieties, then there exists a semi-orthogonal decomposition, some component and X. So essentially, this is telling you that not only is this an inclusion of some subcategory, but in fact, this subcategory is the piece of some decomposition.
Maybe
this
you need admissible, so inclusion has a left and right joint.
Yeah, but so for smooth predictive varieties, this is automatic. Yeah. Yeah, exactly. So in general, for general categories, you would need for this statement, you would need, I'm not sure if I would be able to say on the spot, this one has to be either left or right admissible. But for smooth predictive varieties, luckily, this is always the case.
But is it clear that given an embedding of dbx to dby, it's always induced by some Fourier-Mukai transform, or because for equivalence this is true, but for embedding I think this is still unknown.
Yeah,
it's not.
In any case, I'm not using this statement. So I think, in fact, the more general statement is if you have the db of x inside some triangulated category, I think it's already admissible.
Okay.
I think it's probably you need some finiteness condition on it, like being proper or something like this, I think.
Okay.
But I think under mild assumptions, this automatically, yeah.
Okay.
I think this follows from, there's this paper by Bondal and Orlov, representability of functors and Serre functors and something like this. I forget the title. And they show that this guy has some nice properties, and this, I think you also have to use some more recent results of Van der Berg showing that it's saturated. And yeah, I think this is true. But yeah, like you said, usually this will be given by geometry. So actually we have other ways to see it, but yeah. Right, but let me now finally define what this means. So this means the following. So A and dbx generates dby as triangulated category. So implicitly, I am saying that both A and dbx are triangulated subcategories. And the smallest triangulated subcategory containing the two of them is the whole derived category of y. Right? And the other condition is this semi-orthogonality. Let me at least write it once. Yeah. So the other condition is the semi-orthogonality, which you can remember by drawing this arrow here. And then you just put it like this. So there's no non-zero homomorphisms from right to left. So from B to A is 0 whenever B is this is not. Yeah. Right. So whenever you have such an inclusion, you will get such a decomposition. And because of this decay hypothesis, whenever you have some MMP operation, you expect to see such an inclusion. So the expectation is MMP gives you some orthogonal decompositions. So that's a bit the expectation, yeah. Whenever you perform some MMP operation, like the blow up here, you should see some semi-orthogonal decomposition. But this is at this point only a very, very far-fetched expectation. Yeah. Okay. So the next thing I'd like to do is to see some examples where this expectation is true, if fulfilled. So some evidence for this thing. So let's recall operations we have. So Mori fiber space, which is some kind of projective space vibration or Fano vibration maybe. We have divisorial contractions, which are the blow-ups that we had before. And we have some weird stuff, which is called flip. Well, this is weird for me because I don't work so much with, or I don't work with flips at all. Right. So these are the basic operations. Another question is, for which of these basic operations do we know that we have semi-orthogonal decomposition? It's probably too high, right? Okay, so examples, and maybe the first example is with Bailinson in 73, 78, I think. So this was the first example of this kind of decomposition. So in a way, it's what started this whole business. Okay, I'm gonna explain now, sorry. Okay, so I need to give two explanations. First of all, here we have a decomposition with more than two pieces. And what I mean is, again, they generate the category as a triangulated category. And whenever you have a piece which is on the right of a piece on the left, there's no morphisms. So here there's no morphisms. Here there's also no morphisms. Here there's no morphisms. I hope it's clear. That's the first clarification. The second one is I'm just writing the derived category of a point, but this means that there is some subcategory here. So I'm not saying how they are embedded here, but I just want to make it more obvious that we're really chopping up this category into categories of smaller varieties, let's say. But you should be precise about how they are embedded in, yeah. And I think this was something like the bachelor thesis of Bailinson, so it's pretty cool. Yeah, very nice. And this was kind of the first example of this decomposition. And some follow-up was Orlov in 93. And Orlov generalized this to the relative setting. So this is kind of a silly example of a Mori fiber space where you just contract Pn to a point. So it's some kind of Fano vibration. And Orlov generalized this to some relative setting. So should at least say this is n+1. And this, so now you take some rank R vector bundle. And then you get R copies of this guy. And this generalizes this because you would take some n+1 vector bundle over a point. Yeah. Okay, so this is again a Mori fiber space. I think R, yeah. Yeah, I always have to think, how is this a generalization of this? Yeah, I think it should be R. Right. And in the same paper, Orlov proves the blow-up formula. So now let's say you have Z and Y smooth projective varieties. And let's say Z is a closed subvariety of codimension C of Y. So this is a closed subset of Y of codimension C. And then you have the composition, the blow up along Y, sorry, along Z. This is C minus 1. Oh. So in this case, you get a bit more complicated decomposition because, well, there's more players involved. So you have on the one side the components which are given by the center of the blow up, and then you have a copy of the variety underneath. Yeah. And so how does this relate to previous things? So for example, okay, one first good reality check. If you blow up something of codimension 1, you're not doing anything. That's good. Good reality check. Another thing is when you blow up such a smooth subvariety, you get some Pn or PC minus 1 bundle over the center. And then kind of you apply this kind of result to see the decomposition you see on the left. So this is also the reason why it was in the same paper, I guess. And yeah. So they're related statements. And this gives us divisorial contraction. Another one of these MMP operations. And just to mention one example of flip. So this can be found in Huybrecht's book. And it's called the standard flip there. And okay, I just draw the diagram, something like this. So you have some variety X, and inside X you have some copy of PK. Here you have X prime with some copy of PL. And the starting point is this X tilde actually. And you have inside of X tilde a copy of PK times PL in such a way that you can contract either of them. So here you can contract PL and here you can contract PK. And so let's say L is less than K. Yeah, and whenever you have this variety embedded here with a nice normal bundle, then you can contract either way and you get what is called in this book the standard flip. And in this situation, you will get a decomposition dbx prime. Right, and the important thing is that this is not zero, yeah? So it's non-trivial decomposition. Right. And you also see that if this is just a point, you get a generalization of this one as well. You also would get some kind of generalization of the blow-up situation, a very particular blow-up, but still. Right, so that's another example. So now we have one example of each kind of MMP operations, right? So that's really nice. Let me stress this again. So every time I'm writing these decompositions, I'm just saying each of these components is equivalent to the Dirac-Katter of the center or the one of Y, but I'm not saying how they are embedded. Yeah? So because I just want to emphasize how the varieties fit into each other. Okay. So I hope that's not confusing. And one last. You get an equivalence. You get something called the flop, and I don't know if it's also called the standard flop, but yeah, and you also get, although, yeah. But does it depend on X tilde, what X tilde is? Huh? Analytic local is the T of nice. So they have the big dimension something. Okay, never mind.
So when the k equals L equals 1, then S is still that has dimension. So P1, PK times PL larger.
Aha. Yeah. That, didn't realize that. Yeah, sure. Yeah. Right. So let's mention one last piece of evidence, let's say, because there's Kawamata in the 2000s. So there's an ongoing student seminar on toric MMP. So I think it's relevant to say, so the conjecture and the expectation are true, hold for the toric MMP. So for toric MMP, everything is known. And this was work of Kawamata. Right. So this is or these are some of the pieces of evidence that we have for these things. But now maybe let's discuss, well, first, what is one of the main ingredients, and second, what are some of the problems that appear? So hopefully, okay, so that was the evidence or some of the evidence. So main ingredients are two, or I would say are two, because you see that actually this blow-up formula is very related to this one here, right? The projective bundle formula, which is in turn like a generalization of this. So I would say like the main ingredient of this, and the main ingredient is Kodaira vanishing. Whoops, this poor guy died. Kodaira vanishing or Kawamata Buick. Vanishing. And essentially the problem is that I didn't tell you how these guys are embedded in the big category. But this Kodaira vanishing is what is going to guarantee that there is no morphisms, non-zero morphisms from here to here. Because for P1, you would get dB of P1 is something like some category generated by this, and then some category generated by this. And then the computation that we did before shows that this is just 0 by by Kodaira vanishing. Although using Kodaira vanishing here is.
But then you need a characteristic 0.
Yes, that's a very good point. Yeah.
But anyways, for Pn, we don't need.
Exactly. Yeah, I was saying like using Kodaira vanishing here is almost circular, right? You would just check homology. Yeah. But that's a very, I'll come back to this, I think. Yeah. To the characteristic 0 thing. The other ingredient is, which is not so obvious, but I'll ask you to believe me, I think. Adjunction. It's the adjunction. This means hom is the same as hom, like this. And this is one of the key ingredients as well. So you can use these adjunctions to construct these semi-orthogonal decompositions. And these two are important ingredients of this kind of theorems that we've seen before, this kind of evidence. Right. So these are, so now, of course, the question is, in which situations do we have these results or not? But something that I haven't talked about yet, and I should talk about, are singularities, right? Because we're doing MMP, so we want to, or we don't want to maybe, but we have to look at singular varieties. So let me say problem are singularities. Yeah, and in fact, singularities are going to be a problem for this second part here. So let me briefly explain this part. So if X is singular, then you have some non-trivial category, subcategory, so dBx. And this is always Okay, so this is where it becomes important that I say this is bounded. So this always sits inside the unbounded derived category of quasi-coherent sheaves. And in the singular case, here we have a non-trivial subcategory, which is given by what are called perfect complexes. So these are complexes. It's a full subcategory, and the objects are complexes locally quasi-isomorphic to bounded complexes of vector bundles. Right, so the important part is that this is a non-trivial subcategory. And now what happens with, so let's pretend that we don't have any problems, yeah? So now what happens if we do this kind of adjunction on one of these categories? Let's say we apply to this. Well, as long as this guy is proper, then we don't have a problem with this. This is inside this guy here, inside, probably I should write if it's morphism from y to x, from x to y. Right, so in this direction, there's no problem, but if we pull back, then we have a problem. Because implicit, so
not include.
yes, thank you. Yeah, exactly. Because so I'm not being explicit in the notation, but this really means the derived functor, the derived pullback, because otherwise it's not a functor, triangulated functor between these guys. And the problem is that when we have singularities and we now try to pull back some complex, some bounded complex on y, first we have to find the locally free resolution and then pull back this locally free resolution. But this locally free resolution is not going to be bounded. So we're gonna land outside of the bounded region. So this is a problem. And then you can say, okay, let's try to use this one, right? And then we have the opposite problem. So this one is still inside of this guy, essentially, because if you pull back a line bundle, you get, yeah, you don't have to do much here, but there's no reason why pushing forward will be compatible with this. And indeed, you have a problem with this, yeah. So here, it doesn't matter which one you want to pick, you run into trouble. So you run into problems with the adjunction, yeah. So these are the kind of problems that appear when you try to do this for singular varieties. And so, in fact, part of the problem of this decay hypothesis in the singular setting is to figure out which category we want to look at. It's not clear that we want to look at this or something completely different. For example, Kawamata for toric varieties, which also have some singularities sometimes, he does something completely different to these two categories. Yeah, so that's part of what I want to emphasize is that this is part of the problem, figuring out which category we want to look at. Yeah. Okay. But the singularities themselves are not a problem. So let me see. Depending on the time. Okay, so we have time for that. Right, so the singularities themselves, they are minimal model program singularities. So in terms of Kodaira vanishing, they are not a problem. And just to give an example, I can use the chance to mention a previous theorem. So if you have a Fano fibration, so this means fibers are connected. What else? The dimension of x is dimension of y minus kx is ample over f with. So now you assume some singularities on x, but you assume MMP singularities. So these are not completely uncontrolled singularities. And now you assume y is smooth, which is now not a nice assumption, but I'll say more to this. Then you do have some decomposition. And again, the important thing is that this guy here is non-zero. So now you have some more general Mori-Fiber space with some singularities, and you always get such a decomposition here. So singularities are not the end of the world. Here, really, the end of the world is also not the end of the world, but the problem is the adjunction. And this is why we need smoothness here. So if y is smooth, then we actually don't have a problem here, because pulling back this category agrees with the perfect one. So we're also gonna land inside the correct category.
So do you really need the assumption on the dimension? So can
Uh,
x equal to dimension y?
So to make sure that this guy here is non-zero.
But if you blow up, this is also an example where, yeah.
So if you blow up, how is minus?
Yeah, for instance, if y is smooth and you blow up a point,
Yeah.
then this is maybe still.
You mean the statement here?
Yeah.
Yes. But okay, this is maybe part of the problem because I'm not saying how they are embedded. Yes, but so in the case of a Mori-Fiber space, the structure shift here is a relative exceptional object, which means if you push forward the local home, you're gonna get something which is only concentrated on degree zero and like a just one dimensional. And I'm not sure if in the blow up, because in the blow up, it's not true that the composition is given by exceptional objects. Okay, yes, the center, yes. Center is an exceptional object, but so I wouldn't know how to use the same proof.
So Fano fibration just means that a general fiber is Fano.
Well, I'm asking minus kx is f ample. It's a bit more restrictive, I guess.
But it doesn't need to be like, for instance, equidimensional or flat.
It doesn't have to be. Actually, this is the harder part of the statement. I mean, so not that, but yeah. So the one where you have to work a bit more is to show that you don't need the flatness assumption. So similar statements were known if y is a point. It was known that for KLT varieties this works, and if these two are smooth projective, it was known for flat Mori-Fiber spaces. But you can actually get rid of the flat, yeah. But I wouldn't know how to use the same proof for blow up and this.
Oh, really?
Yeah. But maybe, yeah. And I mean, maybe you actually have a proof in mind already. You can maybe discuss. We can discuss later. Okay, but maybe I can discuss later and see if. But related to what you asked before, so this works for over k of characteristic 0, not necessarily algebraically closed. But there is some from the point of MMP, there's some interesting class of varieties in positive characteristic, and these are called F-split varieties. So this is remark by Nasconi. And it's really only a remark, but the same works for F-split varieties over a finite fields of positive characteristic. So if you assume certain conditions on your variety in positive characteristic, then you can ensure that Kodaira vanishing works. And as soon as Kodaira vanishing works, essentially the same argument is going to give the result. Yeah. Any other questions? Okay, so this is the whole context of MMP and semi-orthogonal decompositions. And now we want to talk about the other side of the coin, which is the lack of the non-existence of decompositions. Right. Actually, related to non-existence of decompositions. Okay, no, maybe not. Maybe I'm not. I hope the Blackboard is still readable. I feel like it's getting more and more unreadable. Sorry. Okay, so this is the other side of the question. So for which smooth projective variety X, for which varieties is it the case that there is no decomposition? So by which I mean no non-trivial composition. Because strictly speaking, you can always take 0 as one of the, right? And let's call this guy so semi-orthogonally indecomposable, Si. So which varieties are semi-orthogonally indecomposable? And because of the previous discussion, so let's say chapter 2 implies X should be minimal. So right, this is because of the expectation. If X is so minimal in the sense of the MMP, so F. And that's because of our expectation. If we have something which is not minimal, we can perform some MMP operation, and then we're gonna expect to see some semi-orthogonal decomposition happening. So if we want to find varieties for which no semi-orthogonal decomposition can happen, we should look for minimal varieties. So we should look among minimal varieties. Right. So is the question clear what we're looking for? We're looking for smooth projective varieties such that the derived category doesn't have any non-trivial semi-orthogonal decomposition. So let's start with a positive example. Just due to Bridgeland. And this tells you that if the canonical divisor is 0, so if the canonical line bundle is trivial, then the variety is semi-orthogonally indecomposable. Okay. So maybe let's try to see why. And yeah, so hopefully this serves as a good review of this Serre functor that we mentioned before. So this uses the following fact. So the proof uses the following fact, which is also due to Bridgeland. Also same paper. So the fact is that if dbx is A plus B, then either A is 0 or B is 0. And this works for any connected scheme. So my notation is bad because, but it works for any connected scheme. If in particular it works for X. So if we can find a decomposition in such a way that not only there is no non-zero homomorphisms in this direction, but also there is no non-zero homomorphisms in this direction. So this is what you would call a orthogonal decomposition. Then it follows that one of the two factors has to be trivial. So there are no non-trivial orthogonal decompositions. And this is true for every smooth projective variety, irreducible variety. So this is what we want to use. So given dbx suffices to show dbx is the other way around, right? So we're assuming that we have some semi-orthogonal decomposition. So there's no maps in this direction. We want to show that there's no maps in this direction, yeah? So we want to show that dbx is also can be written like this. So we take an element in B, an element in A, and then we show that And then we show that there's no non-zero morphisms. So we should show that this guy here is 0, right? No, we should show that this one here is 0. Suffices to show that that is a composition. So we want to show that this guy is 0. And now we have the Serre functor. So we apply the Serre functor, which tells us this thing now. And we want to show that this is 0. So if this is 0, then we're done. So what is the Serre functor? We said it was tensoring with a canonical line bundle, which in this case is the structure shift, and then shifting by the dimension. So tensoring with the structure shift is not doing anything. So this is just the same as hom from B to A, and then we shift by the dimension. I should put here this. Right. And now we started from the assumption that this is a semi-orthogonal decomposition. In particular, A has to be a triangulated category. So this shift of A, which is an object in calligraphy A, has to be inside A. And this guy here is still an object in B. And then because we had this decomposition, this has to be 0, yeah, by the original SOD. Because, yeah, that was just the assumption. We were assuming that we have this decomposition, and then we show we also have this decomposition. Right. And maybe here we're using everything is a finite dimensional vector space. Okay. So this was kind of one of the first examples of in the composability in this sense. Any questions? So here, the key was to use this knowledge that we had about the canonical bundle. So more generally, one of the main tools to prove this is the following theorem. Oops. Oh, I did it this way. Okay, so the theorem is due to Kawatani and Okawa. And appeared in 15 in the archive. And the theorem tells you that, I mean, it tells you much more, but I'm going to give a simplified statement. So if X is smooth projective variety such that the base locus of the canonical is a finite bunch of points. This is very bad language, but finite bunch of points. No, this is misleading. If it's finite, but okay, if it is supported on a finite set, so it could be empty. That's what I want to. Then it is semi-orthogonal in the composable. And this is an extreme case, right? Because the base locus is just 0. Sorry, so you have a section here which is just non-vanishing section, so the base locus is empty. So this is one of the main theorems that you can try to use if you want to show that something is indecomposable. And yeah, because of this, there is the following conjecture. So maybe this is something I said at the beginning, and now finally there's some evidence for that claim. So semi-orthogonal in the composability is very related to canonical divisor. When I said that MMP and this sequence of categories are both very related to canonical. Right. And this motivates or partially motivates the conjecture. That is the one that we were actually interested in this talk, finally. So smooth projective variety. The minimal smooth projective variety. Then write it here. If the geometric genus, which is H0, is non-zero, then it is in the composable. Okay. Yeah, and this is finally the conjecture that we care about in the title of the talk. Okay, so you have a minimal smooth projective variety. And if you have a condition on the geometric genus, which is kind of related to this, because if the geometric genus is zero, then your base locus is just everything. But if it's non-zero, then the expectation is that you cannot find a decomposition. Okay, so is there any question about the conjecture, about the statement of the conjecture? So maybe you can ask, okay, yeah, I see why this is slightly related to this, but actually, why do we need this assumption? And then maybe we can give an example. And this is the Enriquez surface. If it's empty, then the theorem holds, and if it's empty, then you.
But for Enriquez surface, then.
No, there's no selection. The PG is zero, right?
I mean, Kawatani, Okawa, there's no assumption on PG.
Right. There's no assumption on PG. And for the Enriquez surface, the geometric genus is zero. So the base locus is just.
But, I mean, for Enriquez surface, is it indecomposable or?
No.
Then.
The base locus is everything, right?
The base locus.
It's the empty intersection, which should be like everything.
I
guess.
Empty intersection is everything.
I mean, I guess depends on how you define it. But so if this base locus of omega x is, maybe I think I would define it as the non-zero sections.
I see. So the assumption implies in particular that PG is positive. The assumption on the base locus implies that there is section. There is global section.
Yes, unless it's a point or something. Yeah. So I would define this as the vanishing loci of S as a topological space.
Okay, thank you.
Then I think it should be interpreted as being everything if. Yeah, you're right. So if implicitly you're But exactly, this is a very good example. So the Enriquez surface is not semi-orthogonal in the composable, and the geometric genus is in fact zero. And maybe write it here. So then maybe you want to rule out this case. So then PG greater than zero is a necessary assumption, by which I mean that if we just forget about this and we state the conjecture without any other condition, then it's false. That's a counterexample, yeah? But I've said this is a necessary assumption, and let me immediately contradict myself. So is it really a necessary condition? So the question for minimal varieties, blah, blah, blah. So for minimal smooth projective varieties, is it true that being semi-orthogonal in the composable implies that the metric genus is bigger than zero? So is it really a necessary assumption? And the answer is no. So this sentence is a bit sketchy. Yeah, and this is finally the example that we're interested in. So this is given by bielliptic surfaces. So bielliptic surfaces, they are indecomposable, but the geometric genus is 0. Yeah. And yeah, so in this sense, they provide an interesting example, because here we're really having this is the big conjecture in this business. So you have this kind of, or is a conjecture in this business, and you have this assumption here. And then it is, of course, important to know that it's not a two-way street. So you cannot go the other way around. So bielliptic surfaces are semi-orthogonal and decomposable, but the geometric genus is 0. And then the question that we ask is whether this can be generalized. So to higher dimensions. Yeah, so can this be generalized to higher dimensions? Okay, so is it clear why this example is kind of telling you that the converse is not true? So and as you pointed out, in particular, this gives you an example of indecomposable things where you cannot apply this to deduce the. Right. Sorry about the noise when I breathe. Okay. So this is the work in progress that I was talking about in the beginning. And let me start by defining the class of varieties that we are using to try to generalize this bielliptic. So definitely, okay, and the answer is yes, but currently to some modest extent, but hopefully to a larger extent in the future. So definition, hyperelliptic variety is a quotient of an abelian variety A by a finite non-trivial subgroup of automorphisms, in the sense of, maybe to make it clear, let me just write by holomorphisms of the abelian variety. So automorphisms which are not necessarily group homomorphisms with respect to the group structure, acting freely and without translations. And okay, the definition is a bit long, but maybe a quick way to think about this, guys, is to think of something which is not abelian. So it's not an abelian variety, but it's close. So admits an abelian variety. Abelian variety. As a finite état cover. So it's not abelian, but it's pretty close to being something like an abelian variety. And bielliptic are an example of this, where the abelian variety would be a product of two curves, or two elliptic curves. Right. Yeah, and okay, maybe I'll just directly say, now let me define it. Okay, so it's called, so a hyperelliptic variety is called irregular if the H01, which is Q, is greater than 0, and abelian, which is a very confusing name, but let me just use it. Maybe I'll use commutative. Yeah, that's better. Commutative. If G is commutative. And I should say G is determined by the quotient, by A over G. Okay. So a priori not so clear, but in fact, you can express G as you have some hyperelliptic variety. You know, it's the quotient of some abelian variety by some group, but it could be the quotient of a different abelian variety by a different group. But this is not going to be the case. So you can write G as the holonomy group of the underlying Riemannian manifold. Okay. So now the expectation or maybe theorem in progress of the people that I mentioned in the beginning is that irregular. And maybe now let me add some safety assumptions. Maybe let's say low dimension or dimension less or equal 4, commutative, hyperelliptic. Varieties are semi-orthogonal indecomposable. Okay. And hopefully this will work in a greater generality, but I think for now we need these safety assumptions to state something that is, yeah. Right. So the main ingredient. Okay, so I didn't say it, or I said it, but let me say it again. And in this way, this kind of result generalizes this example to higher dimensions, right? So now we have some higher dimensional examples of the same kind of phenomenon, because this was not restricted to surfaces. This is just a statement in general for arbitrary dimension. And before we only had an example with surfaces, and now we have some more examples. And the main ingredient is a theorem, recent theorem of Piroshkov in 20. So let's say you have a morphism which is flat. And now I'm gonna use some words, but if Y and all fibers of F are very semi-orthogonal indecomposable, which is something I'd rather not define, but if they're very, very, very semi-orthogonal indecomposable, then so is X. Very indecomposable, and in particular indecomposable. So this roughly means that all subvarieties are also indecomposable, something like this.
So when we say all fibers, so for a singular fiber, which category do you?
So I think this theorem is not really restricted to the case of smooth projective varieties. But
yeah, so just
so the statement is for all closed fibers.
Yeah,
that's what is written in the statement. Yeah.
Maybe I wanted to ask, what do you mean by indecomposable? If the
which category is?
Yeah.
So it's actually worse, because in this context, he's working with infinity derived category. And I don't know if for infinity derived categories you can work with singular varieties in a better way. I'm not sure if that's the case. If that's the case, then maybe that's. But I think, okay, my naive answer would be the same, the derived category of bounded coherentials, I think, which you can still consider for singular varieties. It's just that it's going to be worse in terms of pullback and functoriality. But I'm not 100% sure, actually. Yeah. Luckily for us, our morphism will be smooth. So. Yeah. Let's see. So now to finish, let me just give the idea of the proof or the sketch or plan of the proof. And the idea is to look at the Albanese of this. So this irregularity is in fact also the dimension of the Albanese variety. So given X hyperelliptic with all these properties, look at the Albanese, which is some kind of canonical morphism into an Albanese variety, into an abelian variety, up to choosing some base point, which in this case, a very nice, smooth algebraic fiber space, so connected fibers space, which is even locally trivial, analytic, locally trivial. And this is due to the work of many people, including actually Professor Chen. So we know it's a smooth algebraic fiber space surjective onto a abelian variety of dimension of lower dimension. So dimension is between 1 and dimension of x minus 1. Because if they were the same dimension, they would be isomorphic, and they cannot be isomorphic. And at least for commutative G, one can explicitly describe this morphism. One can explicitly describe the Albanese morphism of our hyperelliptic variety, and the fibers, they are either abelian varieties, or let's say commutative hyperelliptic manifolds, necessarily of lower dimension. And then the idea is that you can use some induction to go up in dimension, with a bunch of caveats, but this is somehow the general picture of the proof. Right. Any question about this?
So why do you need commutative?
That's a very good question, and I think the reason, so this description of the Albanese is, it uses the commutativity. At least in the case of the commutative, it's a description we're more certain about, and in the non-commutative case, it's not so clear that we have such a description. So that's the reason why this assumption is here. Yeah. So it's a safety assumption, let's say. But I should say also for threefolds, all the possible groups that appear are classified. So these are classifications due to Andreas, actually, Demleidner. He's classified threefold and fourfold groups. And for threefolds, for example, all of the groups that appear except the dihedral group of order 8 are abelian. So there's a lot of them that are covered by this, yeah. Right. Okay, and I think I should stop here. So let me stop here. Yeah. Thanks for attention.
Thank you very much. Are there any questions? Yeah, so I think in general, if you have surjective morphism from a smooth projective variety to another smooth projective variety, let's call it F. So assume that, yes, I think if the derived push forward of the structure sheaf is still the structure sheaf, then pullback is fully faithful. So there is always, under this assumption, there's always a SOD.
If this is the
structure sheaf.
So you mean OY into the RF of OX? Yeah.
Yeah. If this is an isomorphism.
Precisely. Yeah.
Yeah.
Then
I think DBY gives a SOD of.
Yeah, correct. And in fact, this is the thing that one has to prove in the theorem I stated before. This is the way, yeah. So and essentially at the end, you for I equals, okay, this is, no matter how I write it, it's wrong, but so on degree 0, it's just the fact that it has connected fibers, which was an assumption. And then in high degrees, you want to use the relative Kodaira vanishing, so Kawamata field-wave vanishing, and the assumption that minus kx is ample.
Yeah, then I think you don't need assumption on like dimension.
On the dimension.
Yeah. So
okay,
for birational map, it's always, it is always the case.
Aha, nice.
Well, provided x and y are smooth.
Nice.
Yeah, because fibers are connected, so.
Yeah, fibers are automatically connected because of this, right? Yeah. Nice. Thanks for commenting.
Okay, more questions? Or are there some students who want to ask questions? Do you want to ask questions? All right, so then let's thank Pedro again for the very nice talk.
Thanks.
So next week, there will be another same time, same room, another seminar online talk by Ruijie Yang.